Alright, let's take a bit of a different approach to the TinyGP program. Let's run it from the main method, and here you'll see that there's the problem.dat file. You might have to add the full path to it so it knows where to find it on your computer. So here I've written out the full path with the problem.dat. So it says problem.dat, but you'll probably have to type this in. When things first start, you'll see that there's a report with some of the starting parameters on it. I'll tell you about the seed, the crossover probabilities, and things like that. And of course, when you run it, you'll be using the problem.dat file. So here are the default settings, I believe, in the program. And this is all the data we've talked about. So you have each line. Here's an input value, and here's the target value. And that goes all the way down through here for the 63 values that we have. Of course, the first line of the problem.dat file is the header. Okay, let's get things started. Once we start it, right away we see some formulas are being put forth as programs. And so we have right here, we have the initial information. The population size is 100,000, the depth is 5. We've got crossover probabilities and mutations set. And we have the range of our terminals being used, so from -5 to 5 and 100 generations. And the tournament size is going to be 2 at a time. And so it gives you this information. You have the generation, the average fitness of everything. You have the best fitness, and so that's 24. And so this one right here has a fitness value of 24. Now I've added this to say how long it is in terms of its character. Number of constituents. So we have, it says 5, so it's 1, 2, 3, 4, 5. So you can think of it as there's 5 different nodes on the tree, where if you go down to here, there's 53, right? You start counting 1, 2, 3, 4, 5, and then you keep counting all the way to 53. All right, so each generation rolls by 100,000 of them per generation. There's generation 0, generation 1, generation 2, and on down. So this was the best individual found in generation 0. And you'll notice the best fitness, in other words, this fitness of 24 applies to this individual. This fitness of 24.5, a little bit less than 24.6, it applies to this individual here, substantially longer. And so as the best fitness, you'll see it slightly goes down over time, and we want it to tend towards 0. Here I've only let it run for 7 generations, but let's suppose that we take one of these whole formulas and look at it closely. Alright, so here I've let it run for a little while. We got up to generation 32. We got an average fitness of 65, and then we have a best fitness of 3. Alright, so now we take this and we cut that program right here. This whole thing, this is a giant program. You can think of it like a formula that is supposed to map the data of the input and target fields. Now you can see this is a very long formula, but there is some redundancy here that could be cut down. Take a look at this, for example. Here we have 2 values within the parenthesis and divided by one another. That could just be a single value. So one thing we might want to do is write some sort of program to scrunch all these down. And indeed, I've written this. So let's take a look at what this would look like if we got rid of these extra parentheses that could be cut down into values. Here's another one, for example. Right here we've got a couple numbers that could be turned into a single number. So that makes these programs especially long. Now let's cut this one down to what it could be. Think of it as a more efficient program that would give you the same output. Okay, so once I run this by a simplifier routine, this original program here was 920 characters long. This new one gives an equivalent output, but it's only 450 characters long. So we've reduced this by 470 characters. So that's about 51%. So we had 10 subformulas in here, the kind I pointed out, that could be reduced down to single sorts of numbers. And so if you take this and you simplify it, it gives you this, which is a much shorter program, and will give you the same output. So the question becomes, on TinyGP, if you look at the problem.dat file that was given with it, what is the output that you're looking for? After all, this is just a formula, or a program, as it's called, which gives you that output. Let's take a look at that now. All right, well, here are a couple of columns you'll recognize on a spreadsheet. Again, our input values and our output values are the targets. And so what we want to find, if we map out the target column here, well, that's the blue line that runs through. So this is ideally what we're looking for. This is the blue line. And as we've run our equation through, this is the equation we got as an output. So if we were to click here, for example, you can see that this is the equation we saw. I just changed out the A's for the X's so they reference correctly. And so this is the equation or the program that was grown by TinyGP. This is the original, the long one. And then over here we have the simplified version. It's the same thing, but just takes up less characters. And sure enough, you can see right here that the gray line's the simplified one, and it follows the orange line exactly. Now, not quite the same, but they're very close. You can see here they overlap almost exactly, but there's some variance. And if we let it run longer, we'd see indeed that these equations would close up that gap. Now, as we roll through here, we can see that we have a total of 63 lines, and each of these again is from the input and target, and this is what the program gave us, and this is the simplified version. But what you're after is some program which matches your target when you apply the input values to it. And that program, of course, is this right here that we saw originally, that we grabbed from the console screen that was being grown by TinyGP.